Good morning, afternoon, evening to everyone. I don't even know what time of day you're watching this video anymore. Today is Tuesday, April 14th, 2020. We are on Unit 12, Day 4 of our Kinetics and Equilibrium packet. Today, you're going to need out your packet to page 6, and kind of similar to yesterday, you're going to need 6 different colored pencils or markers. You don't have a skill check today. You will get one tomorrow once we've done some more practice with potential energy diagrams. But yesterday, we were working on labeling, if you recall, from page 5, the different components of a potential energy diagram. So that was things like potential energy of reactants, potential energy of products, the forward activation energy, the enthalpy, the delta H, what all those mean. What we'll do today is we're going to talk about how does the shape of the curve change if you have an endothermic versus an exothermic reaction. And then we'll actually do one practice labeling problem altogether. And that's where the colored pencils are going to come in. So please have your notes out to page 6. So yesterday, as I said, we were doing a labeling example of a potential energy diagram, but we didn't kind of talk about, is there a difference between if your reaction is endothermic, meaning energy has been absorbed, or an exothermic reaction where energy has been released. So that's what we're going to talk about today. So at the top of page 6, we're going to start by looking at what side of the reaction will our delta H, which remember is our heat of reaction, going to be found on if something is endothermic versus exothermic. So remember, endothermic means that energy is absorbed or taken in. So that means when we see a reaction, we are going to see our energy in the form of kilojoules written as a reactant. So here's an example. Say you have your reactant. I'm going to write reactant plus energy, your delta H, that will yield your product. So you want to highlight the fact that your energy, let me put my finger onto the highlighter, your energy is on your reactant side for an endothermic reaction. And when I talk about energy, I'm talking about my delta H. So it's written on the left-hand side of the arrow because it's being absorbed. Meanwhile, the heat of the reaction for an exothermic reaction is going to be a little bit different. Remember, exothermic means that energy is being released or exiting. Now, if energy is exiting the reaction, it's going to be on the product side, which is to the right of your arrow. So we would have a reactants yielding our products plus our energy. So notice the energy is now on the product side. So just by looking at a reaction, you can tell if something is endothermic or exothermic. The next thing we need to look at is the sign of delta H. And when I say sign, I mean, is it positive or negative? Now, in a reaction, we don't have minus signs. So you're not going to be able to look at a reaction and tell if the delta H is positive or negative. And when we get to table I more in depth, we'll talk about this as well. But I would like you to note that there is an asterisk on the bottom of table I that you can use kind of as a cheat. So if everyone can take their reference table out to table I took a picture of the bottom of table I, and here's that asterisk. This is going to be kind of a shortcut for you. But what this says is the delta H values are based on molar quantities. That's what you don't really need to know that part. But right here, it says a minus sign indicates an exothermic reaction. So if your delta H is negative, it is exothermic. So that's kind of a cheat. You don't have to memorize that. Use the bottom of table I. So if your heat of reaction is negative, that's exothermic, meaning heat's being released. The flip side is true for endothermic. If your delta H is positive, that means that it is endothermic. So the sign of the delta H will also indicate endo or exothermic, not just the location of the energy in the reaction. Now here's what we really want to get in depth with. This is the shape of the potential energy diagram. On table 5, or excuse me, page 5, our potential energy diagram started with reactants going up to products. But this represented an endothermic reaction, which you didn't know at the time. But we're going to draw what the shape would look like for endo versus exo. So I'm going to draw an axis in my first box. I'm going to do it in this one as well. We're going to show a potential energy diagram. So in an endothermic reaction, heat is being absorbed or taken in. That means that the potential energy of my reactants is going to be lower than my products, because my products are going to be a higher potential energy since energy is being taken in. So if I draw the curve for an endothermic reaction, you'll see that the potential energy of the products is higher than that of the reactants. It's greater. So maybe PE of the products is greater than the PE of the reactants. So that's what your curve would look like to demonstrate an endothermic. Now, an exothermic reaction, heat is being released. So that means the potential energy of our products will be actually lower than the reactants. So this time, my reactants' potential energy is going to be higher than my products. So my curve is going to look kind of like a slide. So the potential energy of my products in this one is less than that of my reactants. So it looks slightly different. It's all about where your reactants and products start. I like to think of this as climbing up a short set of stairs and then going down a slide as I read left to right, like I'm exiting. So exit down a slide. Awesome. So we kind of just went through looking at a reaction, how we can tell if something is endo or exothermic by the location of the energy on the reactant or the product side. We talked about how the sign of delta H indicates whether it's exo or endothermic, and you can use the asterisk on the bottom of table I as a cheat for that. A negative indicates exo, a positive indicates endo, and how the shape of your potential energy diagram also can tell you if it is an exo or endothermic reaction based on where your reactants start versus your products. So what we're going to do now is we're going to do a practice problem that is on page 7 of your packet. And this is where you want those different colored pencils in hand as we go through this. So here is the practice problem on page 7. It gives you this potential energy diagram, and it would like you to label with arrows and letters for each of these on this chart. And it also wants you to give values, which we haven't done yet. So we're going to go through this kind of together. I would like to remind you, if something touches the x-axis down here, remember that means it is the potential energy of something. Blank. Potential energy of something. All right. Down in the left-hand corner, that should be 0. So you'll notice this scale goes up by 50. So we haven't dealt with the actual values for each of these things yet. I just wanted to start you off by doing the arrows, but we're going to kind of work it in a little bit further today. So I'm going to use red. I like to just go in kind of rainbow order. But we're going to first label the potential energy of the reactants and find a value for that. So remember, potential energy of something means it has to touch this axis. And we're going to do for the forward reaction. So that means our reactants are here. So reactants, I'm going to write R. Products, I'm going to write P. And then remember, up at the top is your activated complex. I think this is the best way to start. Label everything. Okay, so we got reactants, activated complex, to products. So we're going to start with potential energy of our reactants. So potential energy of means that my arrow must touch the bottom, and we're doing reactants, so it's got to stop at the reactants. So that arrow right there, and remember, you could write it over here if you wanted. It doesn't matter where it is left to right. It's where the arrow starts and stops, top to bottom, that is the most important. So I'm going to label this A. Now, the distance that arrow covers, it goes from 0 to 50 kilojoules. So that means the potential energy of my reactants is 50 kilojoules. That's the actual numerical value based on this diagram. So that's your first one. Second thing they want you to label is potential energy of your products. So let's go to a different color. I'm going to go orange. potential energy of something. All right, that means it's got to touch the bottom right here. So I'm going to start my arrow there. And because they want the products, my arrow would end up at the products. And that is the potential energy of my products. Now notice where the arrow starts. It starts at 0 and goes to 100. So that distance is 100, right? 0 to 100, the distance that arrow covers. So the potential energy of my products is 100 kilojoules. Okay. Next one, let's do the potential energy of the activated complex. I'm going to go use green for this. Once again, potential energy of something. So it's got to start on here on the x-axis. And it wants the potential energy of my activated complex, which is way up at the top of the curve. So my arrow is going to end there. And I'm going to draw a line and label it C. The distance that covers from 0 all the way to 250, that is the potential energy of the activated complex. So that total distance from that arrow is 250 kilojoules. Okay. I think the potential energy ones are a little bit easy. I think it's when we get into our delta H and the activation energies it gets a little bit trickier. All right, so we're on to delta H. And remember, delta H is your heat of reaction. The heat of reaction is the potential energy of your products minus the potential energy of your reactants. And you want to remember the term, read between the lines. That will help you. Okay. So remember, these flat lines right here where your reactants start, you can kind of extend that out. Same thing for your products. And the distance between that is your delta H, because it's the difference between my reactants and my products. Now, where you got to be a little bit wary is of the sign of delta H. So on the previous page, we were looking at if something is exo or endo. So if we look at this curve, my reactants are lower than my products. So that matches up with this, which is endothermic, which means my delta H is positive. If it looked like this, if it was exothermic, then my value for delta H would be negative. So since this is, and we can actually fill G out, this is endothermic, I know my delta H has to be positive. So when I write down my value for D, it's going to be a positive value. All right, so let's look at the kind of area this covers. We're going from 50 to 100. So that's a total difference of 50 kilojoules. So that is the heat of the reaction, 50 kilojoules. You could also take the potential energy of your products and subtract the reactants and get 50 as well if you were going to use the equation. Or you can use the chart itself. I like to just use the chart. The arrow starts at 50, ends at 100. I know it's positive because it's endothermic, so it's got to be 50 kilojoules. All right, the next thing they want us to label is the forward activation energy. Remember, forward is reading left to right. And the activation energy, it's not potential energy of anything, so we're not going to start our arrow here. The activation energy is the minimum amount of energy required to react. So we're going to start at our reactants, and our arrow is going to end at the top of that curve, the top of the peak. So that's E. So we start at 50 and we go to 250. That distance from 50 to 250 is 200. So if it helps you to do 250 minus 50 equals 200 kilojoules. That's the forward activation energy, 200 kilojoules. Let's switch our pen again. Let's go to this. We're now going to do the reverse activation energy. That's reading from right to left. So it's not the potential energy of anything, so we don't start our arrow at the x-axis. The reverse activation energy, we're going to start at the products and go to the top of the curve. So I'm going to label that F. So we start at 100 and go to 250, so that's a total distance, of 150. If it helps you to do 250 minus 100 gets you 150, that's fine as well. You don't have to worry about any other value but delta H, it being positive or negative. Everything else is positive. But the distance here is 150 kilojoules. So we've labeled potential energy of reactants, potential energy of products, potential energy of the activated complex, the delta H, remember read between the lines. It's positive because this is an endothermic curve. If it was exo, it'd be negative. We've got the forward activation energy, the reverse activation energy. And then the last question this wants answered is which arrows change if a catalyst is added. Now, a catalyst, remember, does not change where you start or where you end up. It simply just takes this curve and lowers it. So I can actually draw a catalyst kind of does that. If you want to label that catalyst. Now, which curves touch the top of the curve and would be affected by that? Well, E, which is our forward activation energy, F, our reverse activation energy, and then the green line, which is our activated complex. So arrows E, C, and F would be affected by the addition of a catalyst. So this is a kind of question, you wouldn't get it all at once, you'd probably be asked different parts of this to answer. But if they asked what is the reverse activation energy and they want a value, you have to figure out where your arrow starts and stops, and then what does that distance represent. All right, we're going to do one more example problem on the bottom of page 7. This one's a little bit tricky. This is like a bonus challenge type of problem. But this question says, what is the reverse activation energy? So this is what I'm looking for the following balanced reaction, which has a forward activation energy of 60 kilojoules. So they give us this reaction. A plus B, those are reactants, yield C plus D plus 20 kilojoules. So notice 20 kilojoules. This is on my product side. This is my delta H. But it's a product, which means it's being released. So this is an exothermic reaction. And if you recall, as I said, using the bottom of table I as a kind of cheat sheet, if you have an exothermic reaction, your delta H needs to be negative. So that means my delta H is actually a negative 20 kilojoules, which doesn't really matter in this reaction so much, but just kind of think about it that way. When we actually draw this, we need to know this is an exothermic reaction. All right, so I'm going to do a little sketch of this. Okay, so remember, exothermic reaction, think about exiting a slide. It's higher reactants, and then you have a lower product. So this is exothermic. Okay, we can actually start labeling this. We know that the heat of the reaction is going to be negative 20 or 20. So I can actually, remember the delta H, we read between the lines. So this distance right here is 20. Those are horrible arrows. Here's my delta H is 20. They also tell us that the forward activation energy is 60. Okay, remember activation energy from my reactant to the top of the curve is 60 kilojoules. And they want to know what is the reverse activation energy, which would be from my product to the top. So notice, they give me the delta H, which is this portion between the product and the reactant. They give me the forward activation energy, which is from reactant to the top of the curve. So if I wanted to know the reverse activation energy, this total distance here, I simply just have to add those values. So 60 kilojoules plus 20 kilojoules gives me a reverse activation energy of 80 kilojoules. That's a challenge problem. That requires you to know that this is exothermic, that the delta H is negative, meaning that your curve has to look like this going down a slide because we're exiting, and being able to label where the 20 goes and where the 60 goes. If you can't do it, that's okay. It was a challenge problem for you. What we're going to do tomorrow is I'm going to give you a series of 9 practice problems that you can do on a blank sheet of paper to practice with potential energy diagrams, and then you're going to do a skill check. So tomorrow is purely practice, so you want to make sure that you have your notes from pages 5, 6, and 7 all filled out so you are ready to go. Hope you guys have a good one. Bye.